This paper is joint with Yuhta, Ishii, and Xiao, who are both at Penn State. So the motivation for this paper is this observation that we often face different sources of information, and it can be hard to determine exactly how independent they are. So for example, if you seek the advice of multiple experts, and all these experts are using the same underlying data to give you their recommendations, then any flaw in that data can produce a correlated error. And unless you have access to that data directly and you can judge exactly how the experts are using that data, it will be hard to determine what is the precise correlation structure behind the experts' recommendations. So we asked the following question here. How can we make decisions that utilize all available sources of information without leaving us vulnerable to hidden correlation? So before I go over the formalism of the problem, I want to show a quick example to illustrate what this is about. So this example is about COVID tests. The idea is that we have a doctor who receives a patient with some suspicious COVID symptoms. And so let's say that the symptoms of the patient give the doctor a prior belief that there's a 50% chance that the patient has COVID and 50% that they just have a common flu. And the doctor can perform two different tests here, a molecular test or an antigen test, to find out what the what the patient has. And then the doctor has to make some decision of whether to recommend the patient to go to quarantine or no quarantine. And then we have these payoffs here. So the molecular test and the antigen test, they have well-studied statistical properties. And here, these numbers are a little bit made up, but they serve to illustrate that. So here we have the COVID test has a very low chance of false negative. Sorry. A false negative. And the antigen test has a really low probability of a false positive, right? So if you look at these two tests, it might make sense to combine them to, use the strength of both of them. So the problem here is that we don't have any studies, or at least when we looked at it, studies showing what is the correlation between these different tests. And so there's multiple possible correlations we could have here, right? So here I'm now showing this information sources in a different way. Here we have the state where we have COVID, and here we have flu. And here's the joint probability, right? That each test gives you a positive result, or each test gives you a negative result. And so you can see that I wrote these probabilities here in a way that is consistent with what we know from the studies from each test individually. So here, if you have COVID, the probability that the molecular test gives a positive is indeed 90%, as I'm showing you here. So there's multiple possibilities here for what this correlation may be. As you can see here, if I subtract a number from the diagonal and add a number to the other diagonal, this does not affect the marginal probabilities, and it gives me a new possible joint distribution, right? So the question here is, what strategy should we follow without knowing what these alphas and betas are? In this case, what is the precise correlation? So here's one possible strategy we could follow, which is the strategy that says, let's recommend the patient to go into quarantine if either test turns out positive, okay? And indeed, this is the optimal strategy if we assume that the two tests are conditionally independent. But here I just wrote one specific correlation structure that we could have and calculated the payoff of what is that strategy, calculated the payoff of that strategy under this specific correlation structure, and we get a payoff of 1.1. Okay, so this is not bad. Now, here's another strategy, which is much simpler. This strategy just completely ignores the antigen test and looks at the molecular test only. So the strategy says, if your molecular test comes out positive, you recommend quarantine. If it comes out negative, you recommend no quarantine. And so in that case, there's no ambiguity here about what the correlation is, because the only thing that matters to specify the payoffs are the probability distributions of the molecular test. And those are well understood from our study from the molecular test. And we can calculate the payoff of that strategy and we get 1.15. So this is just to illustrate that here, even a very simple strategy that completely ignores one of the tests can actually do better than a strategy that does something more sophisticated, right? What's happening with the strategy that's a little bit more sophisticated, that it leaves you vulnerable to these possible correlations that could happen. Okay, so let me talk about the model in general. And so we're gonna have here a set of states of the world, and we have a prior belief over those states of the world and a set of actions and a utility function that combines states and actions into payoff. And we're going to talk about the utility function together with the set of actions. We're going to call that the decision problem. So the agent faces a decision problem, and the agent has available a number M of information sources here. These are an information source specifies the conditional probability of these signals Yj conditional on theta. Okay, so each information source is a given of the problem. Now, a joint experiment, right? This is a joint information source, if you will, is a mapping that specifies the conditional probability of all the different signals given the state of the world. And this joint experiment the agent faces is specifying what is the correlation between these different information sources, right? And it has to be consistent with the given marginals, P1 through PM. We're gonna let this calligraphic P denote the set of joint experiments that are consistent with the given marginals. Now, the strategy of the agent is gonna be a mapping that specifies what the agent does, what action the agent takes, given the whole profile of signals from every single source, okay? Now, the objective of the agent is to choose the optimal robust strategy. What does that mean? The agent wants to maximize the worst case of correlation that we could have in terms of the expected payoff. So this is just the regular expected payoff that the agent gets from a given joint experiment P, right? Which is a particular specification of the correlation. And we're taking here the minimum over all possible correlations that are consistent with those given marginals, P1 through PM. Okay, so that's the problem. What we want to understand here is what strategies sigma come out of this problem. Okay, so what I'm going to show is that you know, in the paper we have some other results, but here because of the time constraint, I'm going to show just this one result, which is what I want to prove, that with two states and two actions, it is never beneficial to use more than one information source. So no matter how many information sources you have available, you're going to essentially ignore all of them except for one. So you just pick the best information source and you follow that. All right. Okay, so before I go into the proof of this result, I need to go over some preliminaries, a little bit about the Blackwell order, which I think some of you may know quite well, but if you know, then this will be a little bit of a refresher. Okay, so the Blackwell order, here's one way. Blackwell order is about ranking information, right? How much information we have. So one way of doing this is according to what is possible to do, what is feasible. So here I just wrote the set lambda p. This set specifies what is the possible probability distributions over actions given states that we can obtain given an information structure P. So if I give you a P, you have a number of strategies sigma that you could choose. Each one of them is going to give you a different probability distribution of action given states. And the set of feasible actions like that tells you a little bit about how much information you have. The larger the set, the more you can do. So here's how the set could look like. we always have these two corners here available. These are what you get by following a strategy that just basically ignores the information, right? So here I have two actions so that I can plot the probability lambda here on a line. This is conditional state 1, this is conditional state 0. And we always have these 2 points here. This point here is what happens if I just take the same action, no matter the signals that I see. And this point here is what if I take the other action, no matter the signals I see. These 2 points here are what happens if I take a strategy that for one signal, I take one action, for another signal, I take another action. Okay, so Blackwell's theorem, one part of it says that given two information sources, the information source that has the larger set of feasible actions is the more informative one. And it's more informative in the following sense that given any decision problem, the decision maker can obtain a higher expected utility with the more informative information source, in this case P, than with Q. Okay, so this is Blackwell's theorem. Now, if that's clear, I can go over the proof of the result with two states and two actions. So, so first I should notice that we're interested in characterizing the optimal robust strategy here, right? All conditions of the min-max theorem are going to hold in our problem. So if you look at the value of this problem, the value is equal to what we call here nature's problem, which is what we get if nature first picks the worst possible correlation structure against the agent, okay? If nature picks the worst possible correlation structure, then this value here is going to be the same as what we had before. Now, what does nature want to do in picking the worst possible correlation structure? What does that mean? Well, this P is the joint experiment is going to be more informative than each marginal experiment or each marginal information source taken separately, right? That's a requirement. So nature essentially wants to pick the least informative experiment among the ones that are more informative than every single marginal experiment, okay? So here is one place where the two states come into play, because when we have two states of the world, the Blackwell order defines a lattice. So this means that there exists a least informative experiment, which is more informative than every other, every marginal experiment. So moreover, I'm going to need two other properties of the Blackwell order with two states. The other is that with two actions, the two states, two actions are enough for the set lambda P to characterize the Blackwell order. So that means that that picture that I showed you of the set lambda P is exactly really what we need. Larger sets are going to exactly correspond to more informative experiments. And there's one more thing that we need to show, and we do this in the paper, which is that the Blackwell supremum actually can be expressed as a joint experiment. So that, we can write this with the proper marginals. So once we do all this, then we know exactly what is the solution to nature's problem. Nature should just pick the Blackwell supremum, right? And the Blackwell supremum here has a very nice characterization. This is why I showed you this lambda set. So the lambda of the Blackwell supremum, because it's more informative than both P1 and P2, it has to contain the union of P1 and P2. Not only that, but these lambda sets, the set of feasible actions, are always a convex set. So it needs to contain the convex whole of the union of lambda P1 and lambda P2. So lambda of the Blackwell supremum always contains the convex whole here. In two states, we can actually always find an experiment that exactly gives us this convex whole. And so that would give us exactly the Blackwell supremum of these experiments. So that's another very tractable feature of having two states. So this characterization here is going to be very important. We're going to use this quite nicely in a second. So now what we can take, I can talk about the robust value right? This is just an observation given what we've said so far. It's that if I write this value function here, which is what you get in the robust maximization problem of the agent, then this value is exactly what we would get if instead of having all these multiple information structures, the agent had only one information source, which is exactly the Blackwell supremum of all of those, right? This would be just the value of the Blackwell supremum. That would be the nature's optimal strategy. That would give us the same value as before. So that's a useful lemma. Now I can show you this result, exactly give you the formal definition. If we have two actions in two states, then the value, the robust value that we get from having all of these different information sources is equal to just the maximum that we get from each information source individually. Okay, so how do we prove this? Well, I'm going to do this for two information sources. Here we have P1 and P2. We know exactly that the value that the agent gets here is the value that you would get if the agent had exactly the Blackwell supremum. Okay, so how do we calculate this value? Well, we just are basically just maximizing a linear functional. This is just the utility gives us a linear functional in this space, and we're just going to maximize this linear functional here. The maximization of the linear functional is going to give us exactly one extreme point of the convex hull. But now here's the key observation, is that an extreme point of the convex hull has to be an extreme point of one of these sets where we took the union. In this case here, this U here is maximized exactly at this point, which belongs to lambda P2. So this means that if we're going to solve this maximization problem, the payoff that we're going to get with the entire Blackwell supremum is that equal to the payoff that we would get if we only had P2 available, right? So this is the key picture to keep in mind for this result. So this tells us, this, you can always do this, which whether it will be P1 or P2 will depend on the utility function, but the important message is that there always is at least just one experiment that will do just as well as having the entire collection of experiments. So that proves the result. In the paper, we also have some characterization for binary states in multiple actions and for multiple states and multiple actions. So if you're interested in that, you should check it out.